the equations always are basically the same. So let's say if f is a function of, let's say, x1, x2, x3, or x, y, z, what do?
Can you make it equal to 0?
What do we make equal to 0?
The thing that you're trying to optimize?
Thing?
The formula?
What formula we make it equal to 0? Yeah, what do we make equal to 0? Derivatives, right? Derivatives with respect to the unknowns, right? So we take the optimum function that has to be optimized, we take the derivative with respect to unknowns that is equal to 0. Now, if you have, let's say, f of x comma y equals to 5x plus 21, will this approach work? And let's say that I'm asking you, what are the optimum solutions? Where does f achieve the maximum or minimum?
You need to relate y to x somehow. Don't you need to relate y to x somehow?
No, it's a plane. There is no maximum.
What does it mean?
It means that you just keep increasing x and y at x.
Very good. So in this case, so why are you saying that? What is it? What is properties about this f that makes you say that there is no maximum minimum? It's a linear function of unknown, so therefore derivatives will never be equal to 0. Another way of saying it is, where will the maximum and minima be achieved? At the boundaries, right? Whatever the boundaries of the allowable values of x and y are. Does it make sense? Okay, so these kinds of problems where and in addition to that, you can also, so then you can have constraints, right? You can have constraints on x and y. So these kinds of problems where your objective function and your constraints are linear in your unknowns, these types of problems are called linear programming problems. Okay? So we're going to do an example of linear programming today. So let's say that your objective is to design an alloy making made of 3 metals. So let's say there is A, B, and C. Metal A, let's just, well, I guess 1, 2, and 3. Let's call it 1, 2, and 3. No?
Ah, there you go. Right?
In India, we turn the light on by switching it down. In US, you do it up. I always get confused. Okay. What?
That's funny.
It was not a joke. People laugh and I don't say a joke. And I tried to tell a joke, nobody laughed. That was not a joke. Okay, so you have 1, 2. Okay, let's say that you have metal 1, 2, and 3. Okay? And then there's a price associated with each of these. So let's say the price of one, let's say dollars per ton. Let's say 100, 200, and 400. Okay? And let's say these 3 different metals have different properties. So let's say they have different modulus. And let's say gigapascal. So let's say this is 30, 50, and 80. Okay? Let's just not, yeah. So it's material 1, material 2, material 3, not necessarily metals. And then you have, let's say you have another property, ductility index. And this, let's say, is 1, 3, and 2. Okay? And you want to mix these 3 materials to get a material with modulus greater than 70, okay, and ductility index greater than 2. So these are your constraints. Okay? And what do you think will be your objective function? What would you like to minimize?
The money?
Cost, right? The cost of the mixture. So the question is, what should be the fraction of 1, 2, and 3 that you should add to make a material? And we're going to assume that the properties of the mixture is simply going to be the linear combination of the individual properties. Okay, the weighted average of the individual properties. Problem clear to everybody? Okay. So if I move this up and I move the other one down, I should be able to see this. Okay, perfect. Okay? Yeah, everybody's clear with what we're trying to do? So now let's write down what these constraints mean. So the modulus must be greater than 70. So the modulus M of the mixture is going to be 100 times x1, right? Plus 200 times x2 plus 400 times x3. Well, that's the cost. Okay, it's going to be 30 times x1 plus 50 times x2 plus 80 times x3. But rather than working in terms of x3, because we're going to solve this problem graphically, I'm going to replace x3 by 1 minus x1 minus x2. Okay? So this simply becomes,
Dr. John?
yeah.
Did you define x1 and x2 as like the proportion of x1?
Is a fraction, yeah, weight fraction.
Weight fraction.
x1, x2, x3 are weight fraction of 1, 2, and 3. So this will become 80 minus 50 x1 minus 30 x2. Right? Okay. And similarly, ductility index di is going to be equal to x1 plus 3x2 plus 2, 1 minus x1 minus x2. And so this will become 2 minus x1 plus x2. Right? Now we also know that x1, we also have constraints on x1, right? x1 must be greater than 0, less than 1. x2 must be greater than 0, less than 1, right? And also, x1 plus x2 should also be greater than 0. Right? Make sense? Yeah. Yeah, you could, I guess, put it. All right. And let's just say ductility modulus also equals to. No, actually, sorry. Ductility modulus, all these conditions are modulus to be greater than or equal to, right? So this is greater than or equal to. Oh no, this is fine. Sorry, what am I saying? But, so this must be greater than or equal to 70, and this must be greater than or equal to 2. Right? Okay, so we can further simplify this equation. So this will give you 3x2 plus 5x1 should be less than or equal to 1, right? Yeah? And then similarly, actually this equation works out really beautifully. x1 or x2 minus x1 should be greater than or equal to 3. Sorry? No, I put x2 minus x1, right? Huh? Yeah, that's why it should be greater than or equal to 0. Okay. All right, so those are two equations, and then of course, like I said, our other equations are x1 is greater than or equal to 0, less than or equal to 1, x2 greater than or equal to 0, less than or equal to 1, and similarly x1 plus x2 greater than or equal to 0, right? All right, great. So these are our constraints. And our objective function f, which is the cost function, is 100 x1 plus 200 x2 plus 400 1 minus x1 minus x2. This will be 400 minus 300 x1 minus 200 x2. So this is the f that needs to be minimized. Okay? Okay? Yeah, your question? Yeah.
Can you explain what is f again?
F is the objective function. What do you want to minimize? You want to minimize the actual cost of the mixture, right? Because you can see that material 3 clearly satisfies those two constraints, right? So let's say less than greater than or equal to. So material B. So you could just use pure material B. But why would you not want to do that? Because it costs too much. So the question is, can you add a little bit of something else and still achieve these constraints, which will be cheaper than just material B? Okay? All right, wonderful. So the way you solve these problems